If I were to write this and ask you to read that, it looks like we should read that as 5. We're super excited about the number 5. Isn't it a great number? That's not actually how we read that. This is 5 factorial. That exclamation mark gets read as a factorial. And what this means is the product. 5 times 4 times 3 times 2 times 1. So that would be 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1, it's still 120. So 5 factorial is 20. Okay. And that's how we define factorials in most cases. If n is a positive integer, so factorials won't be defined for all numbers. There's not going to be a 5.5 factorial. There's a 5 factorial, there's a 6 factorial. There's not a negative 5 factorial. It's got to be a positive integer for the definition I'm about to give you, and then there's a special definition for 0. Okay. If n is a positive integer, n factorial is just the product. N times the next smallest integer, n minus 1, times the next smallest integer, which would be n minus 2, and we just keep going until we get down to 2 times 1. Now, when I write this, I actually wrote 5 specific factors here. That doesn't mean that n has to be at least 5. Okay, this is just establishing the pattern. I start at n, I multiply by the next smallest integer, I keep going until I get all the way down to 1. Now, if I were to start with 1 factorial would be 1. That's what I start with. I've hit my ending point. That's my last factor too. 1 factorial is just 1. Okay. 2 factorial would be 2 times 1, which would be 2. Okay. So the rule is if it's a positive integer, you just multiply by all the smaller integers until you hit 1. Okay. So that's our definition if n is a positive integer. And 0 factorial, by special definition, is 1. Okay. Now, you might say, but that doesn't make sense. This isn't the definition. This is the definition if n is a positive integer. 0 is not a positive integer. This is a special definition. So this is just by definition. You can't prove it. It turns out it's a good choice. When you get to 3b, you're going to be using factorials a lot, and it's going to be very handy that 0 factorial is 1. But there's no way you're going to get that here, because if you start with 0, the next smallest integer would be negative 1, then negative 2. You'd never get to 1. And you'd have 0 in the list, so you'd get 0. Okay, so this is just a special definition. Okay, we're not going to need factorials a whole lot this semester. We don't have much of the semester left anyway. In 11.5, we're going to talk about the binomial theorem. And I'm going to give you a way of working with that that doesn't require the use of factorials, but there's an option that does involve the use of factorials. And because it is something that occurs in the textbook so that if you're looking through it, you might see it, I wanted to make sure that you were familiar with the notation. So let's just do a quick sum. Let's say I wanted to do the sum as n goes from 1 to 3 of n factorial. So my initial index is 1, and then we're just going to keep going until we hit our final index of 3. Okay. So this will be 1 factorial plus 2 factorial plus 3 factorial. Okay. And we just said 1 factorial is just 1. 2 factorial, I'm just working this out off to the side here, that's 2 times 1, that would be 2. 3 factorial, that's 3 times 2 times 1, that's going to be 6. So this becomes 1 plus 2 plus 6, and that's going to be 9.